And now I wanted to show you the functionalities of simulation, because this is something that is available since the last release we have done. And I wanted to show you here a special part or some details. That's the reason why I wanted to show you that in a new session. I loaded a simple part, which is a tube structure. It's pre-orientated, so I can calculate the regions. I want to use the cell support for that part. And jumping back to the build process and the simulation tasks. So what you have to define at first is the voxel size. This is the simulational mesh size, and it's highly corresponding to accuracy and build time and calculation time. So the smaller the voxel size, the longer the calculation time, but the better the output or the accuracy. For a quick run, I want to double this value, clicking on create. And this is also the thing that I find into the simulation inside AM Studio. It's very beneficial for our customer to have a functionality available to get a feeling how the part will perform during the process or during the build up, and how it will deform during the print job. And it's a sort of sanity check. Is the data preparation that I have done a valid one or not? And now it's finished. And you can have a look at the deformation of the part, and we will see that here in this area and in this area, we have the biggest deformations with about 0.5 millimeter. And I can react on that pretty simple, because I have missed here some supports. These line supports, I did not support it. And by adding here line thickening, block support, and again running a simulation, can you so and again by running a simulation, I can see the effect of the additional supports. So I will find out if I have missed supports, if the supports are not stiff enough or something like that, with this simulation capacities inside AM Studio. And so now the hotspots are shifted to this area here. And yeah. The other thing, this is the sanity check purpose, which is very beneficial with the simulation. The other thing is that you can do a predeformation. And again, running a simulation. Can you? So, and again, by running a simulation, I can see the effect of the additional supports. So I will find out if I have missed supports, if the supports are not stiff enough or something like that, with this simulation capacities inside AM Studio. And so now the hotspots are shifted to this area here. And yeah. The other thing, this is the sanity check purpose, which is very beneficial with the simulation. The other thing is that you can do a predeformation, manual predeformation in this case. What does that mean? When you think about that cantilever, When you print this part, it will deform when you cut it off in a way that you will end up with the blue part. So it will bend a bit due to the inherent stresses which are inside the part. And the idea is we are printing a predeformed part, which is the red one, and we will end up in a valid part. And as long as the simulation is accurate or represents the reality, let's call it in this way, the predeformation of -1. So I take the deformations which were calculated by the simulation and predeform them in the opposite direction by -1. So it's 100% deforming or predeforming. Now I end up with a part which is a bit bigger, because beforehand this diameter was 36 millimeters and now it's 36.58 millimeters, which is more or less nearly the value which we identified. And when I then print this part, I will end up in an accurate part, which will have 36 millimeters in diameter. To get out a valid simulation, you have to do a calibration, and you can find in the orientation stage a load cantilever. So you have to do a calibration of the simulation with your real part and your real machine and your environment. And this is simply done again in the machine settings. There's a description available as well, so you can find how this calibration has to be performed. And the idea is you print this cantilever, you measure, you cut the cantilever from the base plate till to this massive socket, so you do not remove it fully, only to this massive part. And you will end up in a part which is bended a bit upwards. And you measure this maximum set displacement. So you simply measure with the measuring slide, I think it's called, the value before cutoff and the value after cutoff, and the difference, the difference between those two is the max displacement. And this is the input which you simply add here, set displacement, I don't know, for example, 1. And then simply hitting calibration, then this calibration is done in the background. And the simulation will then be calibrated on your environment. This takes less than 5 minutes normally. So yeah, that's it what I wanted to show you.